Hello and welcome to this video for Chemistry 30 Thermochemistry. This is the final lesson of the thermochemistry unit. We're going to talk a little bit about sources of energy and their impact on the environment and globally, as well as calculating efficiency. And then we're also going to look at potential energy diagrams in a little more detail. So first of all, to start with energy. So most of the energy that we have in Canada, our electricity primarily, is coming from processes such as the combustion of fossil fuels, like burning of methane, which is the gas that comes into our homes. It can also, however, be generated through nuclear processes. So some power plants will burn natural gas. Some power plants can undergo a nuclear reaction instead to generate electricity. Either way, both of these methods are going to use the heat generated from those processes to turn water into steam, which is a phase change. So it's important to know how the relative values of energy changes are for physical, chemical, and nuclear processes. So physical changes give off the least amount of energy, usually between 1 to 100 kilojoules per mole, because whenever you're going through a physical change of something like water, that's a molecular compound, remember you're only breaking the intermolecular forces of attraction between those molecules, and those require lower energy than a chemical or nuclear change. Chemical changes are when you have a chemical reaction and you're actually breaking the potential energy the potential energy stored in the bonds of the compounds. Remember, that can be endothermic or exothermic depending on this process of breaking and forming the bonds, which we'll review again a little bit more today. But chemical changes are essentially a medium between 100 and 10,000. Nuclear changes are the largest. A nuclear change is when you actually have the nucleus of an atom splitting apart. That commonly happens with uranium in the radioactive decay of uranium in power plants. And so this gives off millions to billions of kilojoules per mole. If you are ever asked to calculate efficiency, this is something you learned back in Science 9. Efficiency is the useful energy output divided by the energy input times 100. So if we're thinking of a light bulb, the useful output is the light that it gives off, and the input is the amount of electricity that it's using. Okay? These both need to be in either joules or kilojoules as long as they're in the same units, and then you multiply by 100. Note, you should never get more than 100% efficiency, because then you're creating energy out of something, which can't happen. So it's always usually the smaller energy over the larger energy to get an efficiency of less than 100. So we want our vehicles, our appliances to be as efficient as possible, so that we're saving money putting less of an input in to get the same output. Primarily speaking, with the combustion of fossil fuels, we produce carbon dioxide and water vapor, which are greenhouse gases that contribute to the greenhouse effect, the warming of the planet by those gases, and acid rain. The carbon dioxide contributes to acid rain. The more conversions you have, the least efficient it is going to be. Okay, so something that 100% converts its energy, or as close to 100 as we can get, is a furnace. It's about 90% efficient because that energy is mostly just going directly to heat, nothing else. There is some light, some sound that comes off. That's where some of the energy is lost. But that is a much higher efficiency compared to something like a natural gas power plant, which is only 37% efficient, because we're breaking down the chemical energy from the energy stored in the bonds to heating water to convert it into steam. The steam rises, and that's now kinetic energy, which spins the turbine, which is now mechanical energy, and the spinning turbine in a magnetic field generates electricity. So there's a whole bunch of conversions. So every time there's a conversion, you're losing a little bit in the process, usually to heat, if that's not the primary source you're trying to convert it into. So that's why this is a lot less efficient. So we have to assess our risks and benefits of relying on any fuel source and environmental impact. Here's some advantages and disadvantages of using fossil fuels. You already know most of these, but they're relatively low cost, readily available. Our plant vehicles are set up that way. There's expertise, they're affordable, they're used all over the world, and deposits are large. However, as I said, they contribute to the greenhouse effect and acid rain when we burn fossil fuels. They do not affect the ozone layer. The ozone layer is depleted by CFCs, chlorofluorocarbons, from aerosols and refrigerants. the depletion of the ozone layer, if you remember Science 9, does not heat up the planet. It allows more harmful UV rays to come through. The heating of the planet is the greenhouse effect caused by greenhouse gases like carbon dioxide and water vapor. Mining is detrimental to the environment, and they are non-renewable. Eventually, they will run out. So, nuclear power, how much more environmentally friendly is that? They do not produce greenhouse gases, but they do release radioactive waste, which causes other concerns as they can last for thousands of years. Wind turbines is a source of renewable energy, and by the way, nuclear is also non-renewable. Nuclear primarily relies on uranium, and once that runs out, it'll all be gone. Wind turbines comes from the sun indirectly from the uneven heating of the Earth's surface. So it is renewable and it doesn't give out greenhouse gases, but they are noisy and dangerous to birds. Hydroelectric power plants are another source of renewable energy as long as we have flowing rivers, but they can affect the ecosystem on both sides of the dams. There's actually a really good documentary called Damnation that looks at the effect of the ecosystem from the hydroelectric power stations. Now, when we're trying to determine the cleanliness of a gas or of a energy source, we want to look at how much CO2 is released. So if it's releasing 0 CO2, it is the cleanest. So that's solar, wind. Geothermal is tapping into the heat stored under the earth from the hot magma core. You're not digging into the core, but there's heat pockets under the earth that you can dig into. And that's where like geysers are getting their energy from. So solar, winds, geothermal, nuclear are considered the cleanest. If, however, you're looking at a hydrocarbon, you're looking at the number of moles of CO2. So essentially, you're looking at a balanced coefficient, the balancing coefficient. So if I have methane, which has 1 carbon in it, when it reacts with oxygen, I'm going to have to write down here to have space, to make carbon dioxide and water vapor, as long as this is an open system. I have 1 carbon in my methane, so I'm going to produce 1 mole of carbon dioxide. Methane is the least number of carbons that you can have. So it's going to give off the least amount of carbon dioxide and therefore is the cleanest. The more carbons you have in your hydrocarbon, the more moles of carbon dioxide and the dirtier it is. Next, we're going to look, like I said, at potential energy diagrams in more detail. So remember that in a chemical change, we first have to add energy to break the bonds of the reactants. And then when the products are formed, energy is released. Okay, the change is the net effect between those two processes. So in an exothermic reaction, the amount of energy that is being given off is more than the amount it takes to break the reactants. So for example, if I were to look at a potential energy diagram now in more detail, before we knew an exothermic reaction had the products lower than the reactants. However, what about this intermediate step of bond breaking and bond forming? This is what we're going to look at now. So I have to add a certain amount of energy to basically kickstart this reaction, to break the bonds, to separate those atoms into free atoms. And then energy is released during the formation of HCl. Now notice how the purple bond breaking line is less than the bond forming green line. The bond forming is releasing, the bond breaking is absorbing. So we have a net release of energy in this process. Our delta H is negative. Okay? In an endothermic reaction, on the other hand, it takes more energy to break the bonds than is given off when our products form. So before we would draw a potential energy diagram like this, where our products are higher in potential energy than our reactants. But again, if I look at the stepwise what's happening, the bond breaking purple line is greater than the bond forming giving off green line. Okay, so more energy is required to kickstart the reaction, to break the bonds of the reactants than are given off when the product forms. Now this, what we call energy barrier, or what you have to do to kickstart the reaction, is called activation energy. It can be denoted as an E with a subscript A, activation energy. That is the energy required to pull apart the atoms of the reactants. So that bond breaking first step, is also known as activation energy. Okay? It's again the kickstart that you have to add. You have to add energy to make the reaction take place. When you have wood that you're trying to burn, you have to light a match to kickstart that fire burning process, that combustion process. So there's always some activation energy you have to overcome. So when you have a reaction, the activation energy, I don't like that symbol there, these are my reactants, these are my products. The activation energy is always the distance from the reactants to the top of this hill, which is called the activated complex. So this activated complex is like a transitional moment where I have free atoms, doesn't last very long, they recombine to make the products, okay? My delta H is the distance between the reactants and products. So in this example, my product potential energy is less than my reactants, so it's an exothermic or negative enthalpy change, okay? But this activation energy hill always has to be overcome first, the height from the reactants to the top of the activated complex. Same thing with an endothermic reaction. If we look at an endothermic reaction, I have my reactants to my products. I still have an activation energy that I have to overcome, okay? Again, from the reactants to the top of this activated complex. Then my delta H is the distance from the reactants to the products, the net change. So in this reaction, it would be positive, an endothermic process, okay? So again, activation energy is the energy required to break the bonds of the reactants, so it's always from the reactants to the top of the hill. Now, how can we make reactions need less activation energy and therefore speed it up? That's where catalysts come in. Catalysts provide an alternative pathway and lower the activation energy of a reaction. Now, it's said that catalysts are not consumed, okay, because you start a reaction, you add a catalyst, at the end of the reaction you still have a catalyst. But that's not actually true in that it's being unchanged. It is being used in one step, but then it's regenerated in another step. Okay, so this increases the rate of your reaction. So in a certain time limit, you would have greater yield. Now, if you let the reaction go to completion, no matter how long it takes, whether you use a catalyst or not, you will still get the same yield. But this is talking at a certain length of time. You might have more because the reaction is being sped up. Now, one thing to note is the delta H does not change. The potential energy of the reactants and the potential energy of the product stays the same. The delta H is the same. It's just the activation energy that gets lowered. Okay, again by providing alternative pathways. Another example for an endothermic reaction. My delta H is still the same. My activation energy is lowered because of the alternative pathways. It just basically breaks the reaction into multiple steps that require a little less energy than the overall reaction would for breaking the bonds based on the different processes taking place. Here's a sample diploma question. Now, notice how it refers to the forward and reverse reaction. So the forward reaction is reading the graph like we normally would, where I have my reactants to start and my products to end. Now, the catalyzed reaction is always the lower one. So this is your catalyzed reaction because that's the purpose of a catalyst. Okay? This is the uncatalyzed. The reverse process, though, I'm actually going to make it a different color. The reverse process reads the graph backwards, flips the reaction. So these become my reactants and these become my products. So you have to read these questions very carefully. So the activation energy for the forward uncatalyzed reaction. So that's from the height of the red reactions to the top of the uncatalyzed hill. That would be number 2. The activation energy for the reverse catalyzed, so the purple reactants to the catalyzed hill, that would be 4. The delta H for the forward reaction, that would be going down between the reactants to the products, the red ones, so that would be 6. And the delta H for the reverse reaction, going from the reactants to the products, the purple one is going up, that would be number 5. Okay? So hopefully you can understand again how to read this sample diploma question and answer it appropriately. What are some catalysts in industry? Well, we have in our vehicle something called a catalytic converter, and that's exactly what it is. It's a catalyst. It's made of some special metals like platinum, palladium, rhodium, and it makes a honeycomb structure that traps gases. So instead of nitrous oxides being formed when the nitrogen in the air reacts with oxygen, which is a toxic gas, it holds the nitrogen atoms there so they can collide with themselves more to make just pure nitrogen gas, which is not harmful. And carbon dioxide instead of carbon monoxide, same idea, more oxygen to bond with the carbon, because 1 mole of oxygen with carbon monoxide is toxic. Carbon dioxide is a greenhouse gas, but it's not toxic for us to breathe in. When we get into our organic unit, we're going to talk about some reactions like cracking and reforming of crude oil and bitumen to make more marketable fuels like gasoline, and they use commonly sulfuric acid, hydrofluoric acid, and platinum. Last are biological catalysts. Biological catalysts are called enzymes. So in your body you have amylase, peptidase, I can't say that, peptidase, lactase. Essentially these are catalysts in your body, biological catalysts that help speed up digestive reactions and things like that that would normally happen at a slow rate because of the low temperature in our body. And that is it for this final lesson. Thank you very much for watching.